from quantum mechanics to quantum computing. Quantum mechanics is a fundamental theory that describes the behavior of matter and energy at the subatomic level and is an essential pillar of modern physics and technology. Particles can behave as both waves and particles. When not measured, the particle's wave function spreads over multiple possible locations simultaneously. When measured or influenced by external interactions, the wave function collapses and the particle behaves as a particle. The double-slit experiment demonstrates this. When particles are fired at a screen with two slits, an interference pattern appears after they pass through, demonstrating their wave-like nature. This pattern suggests that their wave function travels through both slits and interferes with itself. However, if we try to measure at the slits, the very act of measurement forces the wave function to collapse and the interference pattern disappears. We then only observe particles passing through one or the other slit. The wave function describes the probability of finding a particle in a given location. These probabilities can interfere like waves, leading to areas of high and low probability known as constructive and destructive interference. Even when particles are fired one at a time, the interference pattern still emerges, showing that each particle's probability wave passes through both slits and interferes with itself, forming clear interference patterns on the screen. The strong interference lines that emerge after firing many particles indicate the highest probability of where the particles can be found. This self-interference of the probability wave is known as superposition. In superposition, the particle's wave function exists as a combination of multiple possible locations simultaneously. This means the probability of finding the particle is distributed across these possibilities. Another fundamental quantum property is entanglement. Even when physically separated, entangled particles have correlated spin states. Measuring the spin of one determines the spin of the other due to their shared quantum history. Quantum tunneling enables particles to pass through energy barriers that would be impenetrable in classical physics due to insufficient energy. These quantum properties emerge from the uncertainty principle, which limits how precisely we can measure pairs of quantum properties, such as position and momentum or energy and time. This is because waves do not have a precise position, and particles do not have a single well-defined wavelength, which corresponds to momentum. This uncertainty fundamentally shapes quantum behaviors like superposition and wave function collapse. Now we will see how the quantum principles are applied in quantum computing. Qubits are the basic units of quantum computing designed to harness quantum properties for technology. They can be individual particles such as electrons, photons, or ions, or artificially created quantum units designed to behave like particles and suited for quantum manipulations. In quantum computing, scientists have developed methods to place qubits into superposition, allowing them to exist in multiple possible states, such as 0 and 1, rather than a single definite value. Superposition enables quantum computers to process multiple possibilities in parallel until measurement collapses the system to a single outcome. The process begins by initializing qubits in specific superposition and entanglement states. These qubits are often assigned initial values representing the input of the computation. Quantum gates then manipulate these qubits, modifying their superposition and entanglement according to the quantum algorithm. This manipulation enables the quantum computer to explore many possible computational paths simultaneously. The quantum gates adjust the probability amplitudes of different outcomes to enhance the likelihood of finding the correct solution. When the system is measured, the wave function collapses and the qubits present a single outcome based on the probability amplitudes. Let's examine some applications involving quantum mechanics and quantum computing. Applications of superposition. Parallel computations allow simultaneous exploration of multiple possibilities. Quantum simulations are used to model complex quantum systems, such as molecules. Binary representation encodes qubits in multiple states for efficient data processing. Applications of entanglement. Quantum cryptography enhances security through quantum key distribution with entangled particles, enabling secure key sharing with interception detection. Quantum teleportation transfers a quantum state between particles using entanglement and classical communication. Quantum computing power is enhanced by entangling qubits, enabling more efficient quantum algorithms. Error correction helps detect and correct computational errors. Quantum annealing is a quantum computing technique that leverages quantum tunneling to solve optimization problems, particularly when classical computers get stuck in local minima. Quantum tunneling has applications beyond quantum computing. For example, scanning tunneling microscopy uses quantum tunneling to image surfaces at the atomic level, which is essential for nanotechnology. Some flash memory technologies utilize quantum tunneling for data storage in electronic devices. Current challenges in quantum computing include reducing noise and errors, maintaining quantum coherence, operating at room temperature, improving scalability, advancing error correction, lowering equipment costs, developing specialized materials, and addressing the need for expert knowledge. By leveraging quantum mechanics, quantum computing offers advantages in specific domains such as optimization, cryptography, materials science, and complex simulations. While quantum computing has made significant progress, practical large-scale quantum computers are still under development.